All right, we're going to take a look at 8.1 homework. So the first question here deals with the sampling distribution of the sample mean x bar. And this always has a mean of mu and a standard deviation of sigma over square root n. And these formulas that I just gave you, we're going to use over and over and over again for 8.1. So if you just want to make a note here that the mean of the sampling distribution of x bar is always the regular mean, and the standard deviation is sigma over square root of n. So these guys here are going to be important, especially that one. All right. Question number 2. So the standard deviation, what we just wrote down, of the sampling distribution of x bar is always called the standard error of the mean. Standard error of the mean. So now we'll practice computing. Well, no, this question deals with the idea of the sampling distribution. So suppose a simple random sample of size n equals 38 is obtained from a population with mean of 85, standard deviation of 10. Does the population need to be normally distributed for the sampling distribution of x bar to be approximately normal? So no, the underlying distribution does not have to be normal. So the central limit theorem states that regardless the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases. So this is the one you're going to go with for this question. All right, and so what that means basically is that it doesn't matter if you have a distribution something like this. If we sample from this distribution over and over and over again, okay, and then plot a histogram for all of these x bars, then you're going to see that the histogram of all possible sample means is normal. And that's essentially what 8.1 is about. So now we'll compute the mean and standard deviation. So remember, the sampling distribution of x bar is approximately normal with a mean always equal to mu and standard deviation equal to sigma over square root n. So 10 over square root 38. So 10 divided by square root of 38, and that gives you 1.6222. So we're going to 3 decimal places, 1.622. And we'll practice again, finding the mean. So the mean again is 86. Just the regular old mean, mu. And the standard deviation is sigma over square root n. So 18 divided by square root of 36. Well, square root 36 is 6, so 18 divided by 6 is 3. So this one. All right, so now we'll practice some probability questions. All right, so we've got the simple random sample. Sample size is 36 with a population with mean 76 and standard deviation 6. So we want to describe the sampling distribution. Now what this means is basically we're going to find this over here. We're going to find the mean given this formula and the standard deviation given here. And the distribution here of the sampling distribution of x bar is always going to be approximately normal. All right. And now the mean again is 76. Standard deviation is 6 over square root 36. Well, 6 divided by the square root of 36, which is 6, is just 1. So that's going to be 1. Now we find the probability. So let's do, now here's where we're stat crunch. Now I do want to make a couple of statements here that for 7.2, 8.1, and 8.2, you are going to use the normal calculator for those three sections. So 7, 2, 8.1, and 8.2, these are all going to use the normal calculator in StatCrunch. So let's open that up. And we did. Stat, calculators, normal. All right. And so the mean of this distribution was 76, and the standard deviation is 1. So let's see if we can get this on two screens here. The mean, 76, standard deviation of 1. And we want to know the probability that X bar is greater than 77.7. And we get probability is 0.446. .0446. Okay, and then we'll do less than 73.65. So less than 73.65. 0.0094. Yes, it's just 0.0094. And then we'll do between. So when we do between, we're going to do here. And then between 75 and 77.75. And we get 8013. 0.8013. Okay. As you can see, this is pretty much the same kind of stuff. So here again, mu sub x bar is always equal to the regular mean, which is 31. Standard deviation to 3 decimals is going to be sigma divided by square root of n. So 25 divided by the square root of 100. I'll do this one for you over here. So 25 divided by square root of 100, and that gives 2.5. So 2.5 is the standard deviation. And now we can find some probability. So greater than, so let's type in first our mean and standard deviation, 31 and 2.5. .31 and 2.5. And now we wanted, I believe, greater than 28. So greater than 28. And we get 8849. 0.8849. And now we'll do between. So let's go over here and do between. .1. So between 22.1 and 26.8. 0.463. .0463. And now we'll do less than 28.2. So less than 28.2. And we get 1314. 0.1314. And now we'll do greater than 27. So greater than 27. 9452. 0.9452. Okay, so now we'll do a couple application problems. So again, we've got the lengths of pregnancies of a certain animal are approximately normal with mean 219, standard deviation 22. What's the probability that a randomly selected pregnancy lasts less than 211 days? So now this problem here, if you notice, does not ask anything about the probability of a random sample mean, and that's when you want to use sigma over square root n. So this is going to be just regular old 7.2 question. So we got 219 and 21. So 219 is the mean, 21 standard deviation, and we want less than 211 days. 211 days, so that gives 3516. 0.3516. All right, now interpret this probability. So that basically means that 35 out of every 100 pregnancies will last less than 211 days. So look for the one that says less than, which is here, less than, and out of 100 we would expect about 35. So now is when we come to the sample size. So suppose a random sample of 18 pregnancies is obtained. Describe the sampling distribution. Now remember, this means tell the mean, mu x bar, and standard deviation of the sampling distribution, sigma sub x bar. So the sampling distribution is always normal with the mean equal to 219, the regular old mu, 219, and standard deviation, 4 decimals, going to be 21 divided by square root of sample size. So 21 divided by square root 18. So 21 divided by square root 18, and we get 9497. 4.9497. Now we can use the distribution of x bar to answer some probability questions. So now, now again, the wording here is key because we're asking a probability question, okay, about the mean, right? About the mean of a sample. So when you have this kind of question, probability question about the mean of a sample, then you're going to use this kind of distribution, mean and standard deviation. So less than 211. So 4.4997. 4.499497. And then less than 211. So all we're doing here is changing the standard deviation, which is 0530. 0.0530. Okay, and so again, just look for is less than 211, and this is going to be about 5 out of 100. So you basically take 100 and multiply by this probability, and you get 5.3, which rounds to 5. So exactly 211, 211 or less or more. So we always do, the question said less, so that would be about 5. And then now, again, what do we do here? We change the sample from 18 to 34. So when we do that, we got to change the standard deviation. So new standard deviation will be 21 divided by square root 34. So 21 divided by square root 34, which gives me 3.6015. Okay, so let's go over here, 3.6015. 0615, I believe. 3.60. Let me jot this down here. 3.6015, 4 decimal places. So now we're going to put the mean, which is 219. The standard deviation is 3.6015. And we're going to do less than, still less than, right, 211. So compute that. We get 0.0132. 0.0132. And then out of 100, again, we would expect 1. So exactly more than, less than, so it'd be this one, 1. All right, and so what might you conclude if you were to grab a sample of 34 pregnancies and that resulted in a mean of 211 days or less? Well, the idea here is that the probability is really small. And so if it's not likely to get that sample mean that's less than 211, but yet we got that, then that's pretty strong evidence to say that this true mean is most likely less than 219. So we're going to say that the result would be unusual. So the sample likely came from a population whose mean gestation period is less than 219. So if your probability was large on that last part, then you could say that the true mean is still likely to be 219. All right, part F, what's the probability a random sample of size 15 has a mean gestation period within 10 days of the mean? So within 10 days of the true mean basically means 219 plus or minus 10. So that's going to be between 209 and 229 is going to be the lower and upper bounds. But since we changed the sample size, you've got to change your standard deviation again as well. So the new standard deviation, why? Because we have a new sample size, is going to be 15 divided by square root of 21. So let's compute that. Excuse me. It's 21 divided by square root sample size. So 21 divided by square root 15. So 21 divided by square root 15. And that gives me 5.4223. So we can go over here and change that. New standard deviation, 5.4223. And then we're going to do between. And remember, it's within 10 days of the true mean. So it's 219 here. Make sure I got that right. So it's 219 plus or minus 10. So 219 minus 10, 209. And 219 plus 10, 229. So that's 9349. 9349. 9349. Okay. So same idea as before. You probably get the idea, but I'll go ahead and work through the rest of these for you. Probability that a randomly selected student in a city will read more than 95 words a minute. So again, it doesn't say anything about sample size yet. So this is going to be a regular 7.2 question. So 91 and 10, and then more than 95. So 91 and 10, and more than 95. So that's 3446. 0.3446. Interpret this. So again, just take 100, multiply by the probability, and we're looking for more than. So more than is going to be A, And out of 100, that'll be 34. Okay, now we go to a sample of 12. So we got to get new standard deviation. So let's go ahead and compute new standard deviation, which is always sigma 10 divided by square root sample size. So 10 divided by square root 12. And divided by square root 12. By the way, I'm using Desmos scientific calculator. This is what I recommend for an online calculator. Of course, you can use your handheld, but pretty good one. So 2.8868. So let's go type that in. So the mean is 91. And standard deviation is 2.8868. And then we wanted more than 95. So more than 95, that's 0829. 0829. Okay, and interpret that. So again, we were asked more than, so let's choose the one that says more than, which will be this one. And then out of 100 independent samples, we would expect about 8. So just multiply that by 100 and then round to the nearest whole number. So that would be about 8. All right, so now we changed the sample size from 12 to 24. When we do that, remember you've got to get a new standard deviation. So the new standard will be 10 divided by square root 24. So 10 divided by square root 24. So that gives me 2.0412. Okay. So I'll go over here, type that in. New standard deviation, 2.0412. And then the question was, again, more than 95, so you don't have to change anything there, more than 95, and that's 0250. So probability here is 0250. All right, and then more than, so it'll be about 3. Okay, exactly, more than, so here, about 3. All right, and so what does increasing sample size have on probability? So let's see here. We increase sample size from 12, and the probability was, so sample size of 12, probability was 0.8, and then we went sample size of 24. There we go. Sample size of 24, and the probability went to 0.2. So as we increased the sample size, the probability went down. So increasing sample size decreases probability. It's either going to be A or D. Because the standard deviation, this guy here, will always go down, so decreases as the sample size increases. So this is the one you want to choose right here. All right, so now a teacher instituted a new reading program at the school, and after 10 weeks, it was found the mean reading speed of a random sample of 21 second graders was 93.2. What might you conclude based on this result? Select the choice below. Okay, so what we want to do here is assume that the mean is unchanged. So assume it's still 91, and then look at how likely it is to get 93.2 or more under the assumption that the true mean is still 91. Because if it's likely, we get a sample of 21 second graders who results in an average reading speed of 93.2 or more. Okay, if that probability is high, then the true mean is still about 91. If it's low, this probability we're about to find is low, then that's evidence to say that the new instituted reading program probably had a big effect. So let's go do that. Get our new standard deviation. So it's 10 divided by square root of 21. So let's do that. N divided by square root of 21. And so that's going to be 2.1822. And then the true mean we assume is stays at 91, and we want to know the probability of getting a rate of 93.2 or more. So 93.2 is what we're wanting here. 93.2, and that's well, 1567. So 1567. Now that probability is high, so the reading program probably did not have an effect. So it's not unusual, since the probability of obtaining a result of 93.2 or more is this. This means that we would expect the mean reading rate of 93.2 or higher from a population whose reading rate is 91. Let's see here. How many do we have? Yeah, so let's go ahead and type in our probability that we got. 1567, 1567. And this means that we would expect a mean reading rate of 93.2 from a population whose mean is the true, 91, it's unchanged. And now out of 100, we would expect about 16. So about 16 out of 100 samples, we would actually get an average of 93.2 or higher under the assumption the true mean is still 91. So we'll do 16 here. Okay, now here's a, let's see, this is going to be a percentile question. So there is a 5% chance that the mean reading speed of a random sample of 24 second graders will exceed what value? All right, so let's get our new standard deviation. So again, anytime you change the sample size, you got to get new standard deviation. So 10 divided by square root 24. N by square root 24. And that's the 0.412. Okay, we got that as the standard deviation. To 0.04412. And if it says a 5% chance of exceeding, then that 5% is going to go over here. Okay, that's the probability. The percent of exceeding means that the arrow goes to the right. So that is going to be 94 point, let's see what they want decimal wise here. Round to 2 decimal places, and that's 94.36. 94.36. Okay, so again, repeat same kind of stuff here. Mean is 82, standard deviation 29. (82), 29, and longer than 95. So we get 327. Now we get sample size, so a new standard deviation, which is 29 divided by square root 11. 29 by root 11, and that gives me 8.7438. So that's the new standard deviation. 8.7438. And what did we ask? Probability of what? Longer than 95. Okay, so 0685.0685. Okay. Now again, change the sample size, change standard deviation. So 29 divided by square root 27. 29 divided by square root 27. And that gives me 5.5811. 5.5811. And I'm assuming, I think it was greater than 95. Yep. Okay. So that probability is 0099. Probability 0099. Okay, so again, let's kind of analyze this. What effect does increasing sample size have on probability? So we increased sample size. We had sample size of 11. Probability was 0685. And then we went sample size of 27. Probability went 0099. So we increase sample size. Probability decreases. So probability decreases as the sample size increases. And let's see if they got, see, probability decreases and sample size increases. So both of these here say probability decreases. So because the variability in the sample mean increases as sample size increases. The variability in sample mean decreases as, so we're going to go with this one. So anytime that you increase the sample size, the variability between the sample means actually goes down. So be sure you go with this one here. Okay, and then what might you conclude? All right, so sample mean of 27 time intervals has a mean longer than 95. Well, that was the probability we got here. And again, that's really small. Okay, that's really small. So we probably would conclude that this sample mean is larger than 82. So the population mean may be greater than 82. So that's the one. Anytime you get a small probability dealing with the sampling distribution of the sample mean, that's going to give evidence that the true mean has actually changed. Okay, so again, same type here. Now the sample size, always choose here that the sample size needs to be greater than or equal to 30. And that's just kind of a general rule of thumb. So that's what you're going to do on part A for this question. Now we've got our sample size. So let's compute standard deviation, which will be 3.2 divided by square root 45. 3.2 divided by square root 45. And that gives me 47702. So the mean oil change time is 16.1. 16.1. And the standard deviation, what we just calculated, is 47702.47702. And here you can go 4 or 5, 6 decimals. Sometimes I'll go 4 or 5, but here you can go as far as you can go will be good. It's not going to hurt to go more decimals than needed. And then we want less than 15 minutes. So let's do less than 15 minutes. And we get 0106. 0106. All right, and so here there's a 10% chance of being at or below. And so let's make sure our 45, okay, so we're still dealing with 45 sample size of 45 oil changes. And so 10% chance of being at or below. they get a bonus. So that means 10% is going to go over here. And that time is 15.49. The 1 decimal place, 15.5. Okay, so this time we have the acceptable level for insect filth is 5 insect fragments per 10 grams. A simple random sample. So here's our sample size again, 60 10-gram portions, resulted in a sample mean of 5.7. So why is the sampling distribution of X bar normal? Well, the sample size is 60, so that's more than 30. That's large enough. So the sampling distribution of X bar is normal because the sample size is large enough. Okay, more than 30, but you'll get there. Now you're going to get the mean. So remember, as you see the pattern, the mean is just a regular old mean mu. That's what we wrote down at the beginning. Regular old mean mu. Don't forget that. So that's going to be 5. And then standard deviation is sigma. So square root 5 divided by sample size. And sample size is 60. So square root 5 over 60. Square root 5 over square root sample size. The sample size was 60. So you get standard deviation is 2887. 2887. Three decimals. 0.289. And then we're just finding probability that it's larger than 5.7. So 5.7 larger than 5.7. Uh-oh. Don't forget to change the mean standard deviation. So the mean was 5. Get 1, that's kind of a funny answer. And standard deviation here was 0.289, so 0.289, and then larger than 5.7. So 0077, 0.0077. And this is unusual, less than 5%. So this result is unusual because the probability is somewhat small. And what might you conclude? Well, the probability is quite small, which means that getting this average here under the assumption that the true average is 5 is not likely. So therefore, if we did get this average or more, then that's pretty good evidence to say that the true average number of insect fragments per 10-gram portions is larger than 5. So the result is unusual, so it is reasonable to conclude the population mean is higher than 5. All right, so this time we got a bank teller, spends with each customer, has a population mean of 2.8 minutes, standard deviation of 0.4. So if you select a random sample of 16 customers, so here's our sample size. So again, got to get standard deviation, which will be 0.4 divided by the square root of 16. So 0.4. Or divided by square root 16. So that's 0.1. So 0.1 is our standard deviation. And our 2.8, so 2.8. 2.8 and 0.1 standard deviation, 0.1. And then the question was at least 2.6, which is just greater than or equal to. So at least 2.6. So that's 9772. 0.9772. And then there's an 85% chance that the sample mean is less than. So here's where you give a probability. So the probability is 85% chance, and it's less than, so that means the arrow goes to the left. So 85% chance. So that's 2.9. How many 4 decimals? 2.9036. 2.9036. Okay. And then there's an 85% chance the sample mean is less than. Again, that's probability, but this time we change the sample size, so we've got to change standard deviation. So 0.4 divided by square root of 64. 0.4 square root of 64. That's 0.05. So come over here, change your standard deviation. 0.05. And then put your 85% chance here and less than. And that's 2.8518. 2.8518. 2.8518. All right, and so the last one is the standard deviation. Again, is always going to be the standard deviation. As assumed, standard deviation for this is 40 divided by square root of sample size, a random sample of 20 men, and the average that they spent on Valentine's Day gifts in 2009 is what we're talking about. So go ahead and calculate 40 divided by square root 20. 40 by square root 20, and that is 8.9443. 2 decimal places, 8.94, 8.94. Okay. Less than 130. So let's do our, the mean was 13613. .13. Standard deviation we got was 8.9443, and we want less than 130. So 2466.2466. Then we'll do greater than 140. Greater than 140. 3326. Between 120 and 160. Between 120, 160, 9605, 9605. And then again, this is a 95% of the sample means will be between what two numbers. So again, this is a probability, or you're given probability and asked to find the boundary. So 95 goes here, and between 95 goes here. And we're going to the nearest dollar. So 119 and 154. 119 and 154. Okay, so that's all 13 questions. I hope this helps. You guys take care and stay safe.